In this video, we're going to derive the time-independent Schrodinger equation. In the Schrodinger equation, the time-independent form expresses how a wave function evolves over space. So first, to begin deriving this, we're going to start with the energy conservation equation, which is to say that total energy, which we'll just call E here, is equal to the sum of kinetic energy and potential energy. For historical reasons, kinetic energy is given by the letter T, and potential energy is given by the letter V. So to show the energy conservation of a wave function for quantum theory, we multiply the wave function psi into E, and that gives us the kinetic energy of the wave function plus the potential energy of the wave function. So, psi, the wave function, must satisfy a second-order differential equation called the wave equation. And so that's to say that psi satisfies that the second derivative of psi in respect to a spatial coordinate x is equal to 1 over c squared, where c is the speed of light in a vacuum, times the second derivative of psi in respect to time. And these are partial derivatives since we're depending on coordinates x and t, so we're going to have to use some multivariable calculus to work with this. So psi satisfies the wave equation such that psi in terms of coordinates x and t is equal to a coefficient a times e to the I times kx minus omega t, where k is called the wave number and omega here is called the angular frequency. So let's go ahead and use this here to calculate the second derivative of psi in respect to x. So the first derivative of psi in respect to x, the partial derivative here. So we're only interested in variable x, where t is held constant, and the derivative of a constant goes to 0. So we're only worried about kx here with our exponential. So we pull down a factor of I and k and multiply that into a times e to the I kx minus omega t. That's our first derivative. So then the second derivative of psi in respect to x must then equal the first derivative of this result here, which is to say we drop down another I to get I squared, another k down to get a k squared, times a times e to the I kx minus omega t, which is nice because I squared is just equal to -1, so we get negative I, or excuse me, we get just a -1, so we get a negative k squared times a times e to the I kx minus omega t, which is just equal to our wave function psi. So now what we want to figure out is what this wave number is equal to here. What is k equal to? Well, first and foremost, let's start with what's called the de Broglie wavelength. Let's say we have this arbitrary wave here. The distance of these crests here, these peaks here, is given by the de Broglie wavelength lambda, and lambda is equal to Planck's constant divided by momentum. So we can go ahead and define momentum, P, as the Planck constant divided by lambda. Okay, so normally we define the wave number k as 2 pi divided by lambda. So in other words, lambda itself is equal to 2 pi divided by k, and we can plug this in for our momentum relation. So momentum is equal to h times k divided by 2 pi, where h over 2 pi is the reduced Planck constant, so this gives us h bar times k, and that's what momentum is equal to. So in other words, we can figure out what k is here in terms of momentum. K is just equal to momentum divided by h bar. So now this here is equal to negative p squared over h bar squared acting on psi. Now at this point we want to figure out what p squared is equal to. So we'll use a little bit of classical mechanics, where normally momentum in classical terms is equal to mass times velocity, and we have a kinetic energy in classical mechanics, T sub c, given by 1/2 mass times velocity squared. So velocity here classically then is equal to P sub c divided by m. So in other words, our classical kinetic energy is equal to 1/2 mass times kinetic energy squared divided by mass squared. And right here we cancel out the second power of mass with the numerator of mass to then get that the classical kinetic energy is equal to p squared over 2m. So in other words, we can now solve for p squared by solving this equation here for p squared. So p squared is equal to 2 times mass times c sub c. And now we can plug this in here. So in other words, the second derivative of psi in respect to x is equal to, well, we have a negative here, a negative, what do we have? Well, we have negative 2m divided by h bar squared times this kinetic energy term acting on psi. Okay, so now we want to solve for the kinetic energy, which is T of psi. Rearrange this. We get that the kinetic energy of psi is equal to negative h bar squared over 2m times the second derivative of psi in respect to x. So now we just plug this in to our energy conservation equation to get that the energy of psi is given to us by negative h bar squared over 2m times the second derivative of psi in respect to x plus our potential term. And this here is the time-independent Schrodinger equation for one dimension of space. So in 3 dimensions, which we'll write out as in 3D, we have the energy of psi is given by minus h bar squared over 2m. And now we just have the sum of second partial derivatives in terms of the 3 spatial coordinates x, y, and z. So let's open up a bracket here. We have the second derivative of psi in respect to x, the second partial derivative that is, plus the second derivative of psi in respect to y, plus the second derivative of psi in respect to z, plus this potential term for psi. And this here is just the Laplacian acting on psi. So E of psi, the energy of psi, is negative h bar squared over 2m times the Laplacian of psi times the, or plus the potential of psi. Now, if we were to factor out, bring out this the psi here, we have the kinetic plus potential as an operator, and that operator is called the Hamiltonian operator. So we get the energy of psi is equal to the Hamiltonian operator of psi. And this is a special case of what's called the eigenvalue equation in terms of the energy of the wave function.